So what I will try to do after this introduction by Alberto is to give you a second introduction, but this time about the energy sector, and I try to show you how it works, who are the actors, and what are the dependencies on weather and climate information at large. So first of all, I'd like to thank some of my colleagues, many of them, in fact, and also people from MatNext, Sophie Morel and Julian Stein, and some useful material from Pierre Pinson, and I also made some borrows to make a link with the talks given at ICEM 2011, which was really a great conference, especially from Swap, Jack Gatsfey, Keith Parks, and David Roney. So I really like this picture, which is from the 10-year implementation plan from the GEOS project, which shows the forecast uncertainty as a function of forecast lead time. And in the boxes, you have many processes. Maybe you cannot read all of them because it's quite teeny, but the important thing about this picture is that whatever the timescale you consider, you have processes involved in the energy sector. And so all the timescales are important for the sector. Just some key elements about the energy in the world today. On the left side here, you have the world electricity generation evolution from 1971 to 2010 on the top, and on the bottom you have the consumption. Of course, both are correlated highly, and the interesting picture is that both production and consumption have been rising continuously since the 1970s. And one interesting point is about the red or orange curve there, which is about other, especially renewable energy. And you can see that renewable energy production and so consumption has been rising, especially in the last 20 years, and it will keep on like this in the next decades. The left panel of the slide are for prices. On the top you have the crude oil prices, which are following a global increase trend, even if there are some accidents, especially with the crisis 4 years ago now. And the bottom one is about the price for households, consumers in Europe, and you can see also that the prices are rising. So this is the general context of the energy sector. And the question is, what about the future? These are figures from the World Energy Outlook from the International Energy Agency in 2012. First of all, you can see by the figures there that the total energy demand should rise by more than 40% from now to 2035. So there will be a big increase in consumption, in energy consumption. And if you have a closer look to the change in power generation by energy by 2035 for different countries or regions, what you can see is that there's a small trend for decrease in coal use, for instance, but the most important point in this plot is the large increase which is forecasted for renewable energies, especially wind energy and solar energy. And so basically this means a very important thing with the energy sector towards, in link with the weather and climate science and the energy meteorology, is that energy systems will depend more and more on weather and climate in the future. So just before going deeper, I would like just to make some comments. According to my experience, this talk will be rather about electricity, but there are many common features with the gas systems, for instance. And of course, I will talk mainly of the French and European power systems, and in particular give some examples about the EDF case, so my company. But there are also many common features, processes with other countries, other companies, and so on. And of course, you can find many information on national energy authorities and transmission system operators' websites. I've put some references at the end. So the outline of my talk will be the following. I will first try to show you what is an energy system, a general energy system like the one we have in France and in Europe in general. Who are the actors in such a system? Then I will talk about the processes at stake, or the major ones at least, and then try to show you some impacts of weather-driven uncertainties in the sector. Then I will briefly review some different approaches, show you some examples of the kind of data we use, of the kind of forecasts we use, but I will go very briefly on this as the other talks of the day will be dedicated to the different aspects. As Alberto said earlier, please do not hesitate to interrupt me if you need some clarification point or if you have any question. So, sorry, what is an energy system? Basically, an energy system is designed to provide consumers with electricity, in our case, or gas, if you want. And so it's an ensemble of products and services which have to be delivered to end consumers. These consumers can be big industries, small companies, or households, residential consumers. And for this, of course, you need to produce electricity from nuclear, solar, fossil fire, geothermal, wind energy, and so on. And you need two essential systems, which are first a transmission system. Transmission is concerning the high voltage lines in a country. And then you need a local distribution network or different local distribution networks, which are the low and medium voltage in general. Of course, you also need a strong engineering component. And in countries where you have an open market for the energy system, you need a trading facility. If you want to have a closer look to this kind of picture, you can go to the link I've put there. It should work. Yeah, it works. Nice. And by clicking on the different components, you will have more detailed explanations of all of them, for instance. Okay, so I come back to my presentation. So this is the general picture of an energy system. This is an integrated system, but for instance, if you consider a small island, like we have in France, we have overseas territory in French Indies, in La Réunion Island, for instance, you've got almost the same picture with different kinds of production means and so on, but the general picture is the same. Just a remark before going further about the flexibility of the production means, which is an important component in the management of the system. Here you have a plot from the International Energy Agency publication, quoted there. And this plot shows you four different production means, so coal, nuclear, CCGT is a combined cycle, gas turbine, steam turbine, hydro, and so on. You've got here the proportion of the installed capacity which can respond to variations in the load in the production within a given frame of time. For instance, for 15 minutes, 1 hour, 6 hours, and 36 hours. And on this picture, you can see clearly that some production means, especially hydro, for instance, can answer to quick variations in the load, so quick variation in production, in all the time scales. But you have also means of productions, in particular nuclear and coal, which cannot answer very rapidly. That's to say that you need to plan the increases or decreases in the production for those production means. So who are the actors now? I have already given some information about that, but of course at the end you've got the consumers, so industry, small companies, and residential. You have, of course, electricity producers, and in between you've got the transport system, the transport network at high voltage, and then the distribution networks. In general, it's in plural because you have several networks. For instance, in France, no, I don't know in fact how many there are, but I think it's several dozens. You also have, in general, national regulation authority. In France, it is the CRE, the Energy Regulation Commission. And you also have exchanges of energy with other countries, so imports and exports, which in general are managed by the TSO. But you also have other actors which come in the game, especially, of course, policymakers, national scale planners, insurers, and investors. So you have a large diversity of actors, and all these guys have to work together. I've put another link there, which I think is interesting if you don't know it. It's so RTE is the French TSO, And on their website, you can find the economics application, which shows you in real time the, for instance, this is the demand curve. So we are real. You can see the blue curve is the forecast made yesterday, and the orange curve is the actual consumption. Yeah, I'm sorry. Yeah, it works. And you can see also on this website the actual electricity generation by each production mean. So, for instance, if you move your cursor, you can see the contribution of all the means of production. I think this is quite a nice example of how it works. Well, in most countries where the electricity market was opened to market rules, you have some mechanisms. In French, we call this the balance responsible parties and the balancing market or balancing mechanism. So this consists in a new organization in which so parties who are called balance responsible are in charge of equilibrating what we call their perimeter. So they have customers, they have production means, and they are responsible with respect to the TSO of the after the fact imbalances according to their perimeter. And these imbalances are in fact the differences within their perimeter between the total quantities of power which are injected and the total power quantities which are withdrawn, including all quantities resulting from any transactions on the spot market. In France, we have more than 120 balance responsible parties. I've put some logos of them on the slide. And so you see that you have many actors. And the responsible of all the system is the TSO, so RTE for Réseau de Transport d'Électricité, which is the French TSO. So let's now come to the processes at stake. So I imagine you know or you have understood that power systems are very complex. Here I just recall the figures for EDF in 2011. So for that particular year, we produced a little bit more than 620 terawatt hours. And among this production, there was only 46 terawatt hours from renewables. Renewables are essentially hydropower, but also wind power and solar power. And for this particular year, the hydropower production was quite low because there was not much water in the reservoirs. And what you can see, of course, is that we have very diverse production means with nuclear, fossil-fired, combined cycle, hydro, and other renewables. And all those production means have very different constraints. So you will see after that it's quite difficult to manage. So the basic process at stake for an energy system is to ensure a strict equilibrium between, of course, the offer and the demand. So consumers want to have electricity. You have to ensure the equilibrium between production and consumption at each time step because electricity cannot be stored on a large scale. And so this problem has to be done under many constraints, in particular when you consider the diversity of the production means, which I've given some figures there. So you see we have 58 nuclear reactors in France and more than 250,000 solar installations, for instance. And of course, these problems has to be solved respecting all the constraints, the technical constraints of the production means, but also the financial optimization of production cost constraints. Just to give you an example, if you want to make a day plus 2 forecast with a 30 minutes time step, you have to solve a problem with more than 1 million variables and 10 million constraints. Of course, this problem is very friendly for mathematicians because it's highly nonlinear, non-convex. It mixes discrete and continuous variables and so on. And the fact is that it's also highly demanding on optimality because a 1% difference from the optimal solution can lead to several million euros of loss per year. And of course, we've got to ensure the technical feasibility, because if you don't respect all the technical constraints, you may have outages, disruptions, or even blackouts. So the way it is dealt in France, but it's the same in many countries, is that you have to make an optimization. So you have 3 essential blocks in this process. You've got the production side, the supply side, and the optimization side in the middle. And for each of these blocks, you have some levers to manage your system. For instance, for the production, you can act on the plant availabilities, on the cost of the different production means. From the supplier side, you can act on the retail prices, commercial margins, and market shares, and so on. And maybe the essential one is the optimizer role, was to manage the stocks, for instance, the water stocks in the dams, but also the, I don't know if this word is really English or not, it's quite French. Interruptibilities, by this we mean the possibility for the optimizer to ask some customers to reduce their consumption, for instance, to have better, to be in a better situation when we have a peak in demand. So we have commercial contracts with big companies, but we also have specific contracts with some end residential consumers, where we can ask, let's say, for 20 days a year to reduce their consumption when we have a peak. And of course, they are paid for this. They pay their electricity cheaper in those cases. And so this is really an important component, because it's at this location that we do the optimization and the risk management processes. Of course, this is done with the market means. And so the idea is to optimize this decision making to balance supply and demand in the old portfolio, with the aim of maximizing, of course, the global supply demand gross profit, because we are a company, a business company. And for this, we have to use a risk management policy to guarantee this gross profit and the physical balance of the system. If we have a look at the supply and sales with respect to generation and purchases, you can see that we have different blocks in both of them. On the right side, you've got the supply and sales. So you've got the end customers' consumption. You've got also the self-consumption, which is very important when you run, in particular, nuclear power plants. It requires a lot of energy. So the main consumer is the earth itself. And the losses are all the losses which are in the wires, in the line. Those losses depend on the charge in the line. They depend on the power transiting and on the temperature also. On the market aspect, you have got different structured sales, so that's long-term contracts with specific clients, and we also have wholesale, so spot market and so on, and some specific things in France, in particular the AREN, which is a European rule which implies EDF to sell a part of its nuclear production to competitors at a fixed price, in order to try to favorize the integration of other actors in the French power system. On the generation and purchases side, you've got, of course, all the production from the different production means, except renewables, wind and solar, which are not in this block, because they are here, because there's a process which is a purchase obligation. I think it's the case in many countries in Europe, at least. Because as we want to integrate as renewable energy as possible on the system, EDF is obliged to buy the energy produced by wind farms and solar farms at a fixed price. So it's not really a generation variable, but rather a market variable. And so if we have a look at the risks for this system, first the risk in volume. We have uncertainties. I've put some of them there. Of course, we've got the renewable productions. We've got the river runoff for hydro. We've got the availability of production plants, in particular those which are located near rivers for their cooling. and which depend on the river flow, on the river temperature for the efficiency of the cooling process and so on. But we also have levers, in which I've put in green. For instance, you can play with the startup flexibility of the different production means. You can have some actions on the maintenance, scheduling of different productions means. And of course, the water stocks management is very important. But the system is also dependent on risk prices, especially spot and forward electricity prices, fuels and CO2 prices and so on. So you can see that there are many risks in the system. And if you have a look at them, either in volume or in price, you can easily understand that not all of them, but many of them depend on weather and climate variables. Well, do we have any question at this point? No. So I will now try to show you some examples of the weather and climate-driven uncertainties in energy systems. The first one, of course, at least in France, but I think it's the case in many countries, is the temperature, because temperature has an impact on heating, especially in winter. So I've put several examples there. I will not comment them all, but this one is the 2007 monthly consumption in many European countries. So you have Germany, Italy, the UK, and France. And what you can see is, at least for Germany, UK, and France, you've got a bigger consumption in winters than in summer. Italy is a more flat case. And what is interesting in this curve is that France is quite atypical because the dependence on temperature in winter is more pronounced than for other countries. This is due to the fact that we have a lot of electrical heating in France. The top right figure shows the evolution of the demand in France from 2006 to 2011. So the blue curve is for the raw demand, and the red one is the demand which would have occurred if the temperature was a climate normal. And so the difference between both is the climate effect, if you want. And so what you can see is that this climate effect can vary a lot from one year to another. It can be positive, it can be negative, and it's very important to take it into account. The middle figure, just a typical regular week consumption, where you see that the consumption in the weekend is much lower than in the working days. And the two bottom ones are for typical working days in winter, in January, and in summer and July. And you can see that there is a big difference between both, especially in the evening, where during winter we have a secondary peak due to the fact that people come back home after the work and they switch on the light and they maybe increase the heating. In more details, this should not be like this. Well, anyway, this is the particular case of the winter 2011-2012 in France. So you should have seen the temperature, which is this curve there, and the power demand, which is this one. And the interesting part of the picture is there, behind the color one, but the temperature is somewhere here, and the production is there. So it was very cold in France. We had a 2 weeks cold wave with minus 10 degrees under the climate normal for those 2 weeks. And this plot is the three-dimensional view of the demand during that period. And you can see that we beat several records of consumption. For the first time, the consumption was bigger than 100,000 megawatts in France. It was the first time. And what you can keep in mind is that for a decrease of temperature of minus 1 degree in winter in France, you need an extra production of 2,300 megawatts. And for Europe, for all Europe, it's around 4,000 megawatts. So you can see that France is quite a particular example because we account for more than half the dependence of the European energy system on temperature. Of course, temperature have also an impact on market spot prices. Here you have the figures from the Apex So it is the spot market in France and the spot market in Germany in black, in blue and black respectively. And you can see that during this cold spell in Europe, prices in France increased a lot, especially on these days where they reach more than 600 euro per megawatt hour, knowing that the base load price is around maybe 38 euros at the moment. So temperature has also an impact on prices. Of course, it's not the only parameter which is important. Here I've put an indirect effect, which is due to cloud cover. Excuse me. This is a picture from the 14th of November 2012. Here you have the satellite image at 15 UTC, so 3 p.m., where you can see that we have a lot of clouds on northern France. The second picture is the observed temperature at the same time. So you see it's quite cold on the northern part of France. And this is the temperature forecast error for the same hour together with the cloud cover forecast. And you can see that the cloud cover is largely underestimated with respect to the observation. And so the temperature is overestimated. And this kind of situation with low-level clouds which are present in the morning but do not dissipate in the afternoon are quite frequent in France in winter. At least we have, every year we have at least 8, 10 or 12 events like this. And you can see that the error in the temperature forecast can be very important. Here you have the particular curve for one station, which is Trappes. Trappes is near Paris, so somewhere in this location. The interesting curves are this one, the blue one, which is the observation of temperature at Trappes, and the brown one, which is the forecast made in the morning, so at 6 o'clock in the morning. And you can see that only for 6 hours lead time, we have a forecast error of more than 5 degrees. And 5 degrees is more than 10,000 megawatts error. So it's very, very important. And so cloud cover is really putting a lot of uncertainty on the temperature forecast. And of course, you can imagine that it will have a high impact too on solar production, either PV production or concentrating solar power too. Hydro is another key element of the French energy system, but also in other countries. Because in a country like France, it allows to answer peaks in demand because it's very flexible. But in other countries, like for instance in Canada or in Norway, it is used for baseload. The first plot on the left shows you the 1-year variation of the French total power capacity for hydropower. The black curves are for the climatology, so we have something like 60 years of data. And the curves of the 10%, 50%, and 90% quintiles of this distribution. So the first thing you can see is that we have quite a large internal variability in hydropower production capacity. We also have a strong seasonal cycle with, of course, water incomes mainly in spring with the melting of snow in the mountains and with precipitations in the winter. And the red curve is the one for the particular year of 2003, where we had a strong heat wave in the summer in Europe. And you can see that in addition to the internal and seasonal variability, we can have a very, very strong day-to-day variability. And so this is quite difficult to forecast, and a reduction in the uncertainty of this kind of data is very, very important. On the right side, you've got an article I found on the web from Views and News from Norway. I will not go through it strongly, but the main point is that in winter 2011, the water stocks in Norway were very low, and so they had the higher prices they had never met in the country, and it was reinforced by the fact that when they don't have enough hydros, they use coal to produce electricity, and one of their providers is Australia, and that at that moment in Australia there were floods, and the prices of coal have risen, and so it was reinforcing the fact that the electricity was very expensive. Excuse me. Well, of course, with the introduction of massive wind and solar production in all energy systems, we are depending a lot on wind and solar production, so wind and solar radiation. And one particular problem is linked to the ramping. What we call ramp is a strong variation, a very short, strong variation in amplitude in a very short period of time, either up or down, because in all the countries where the integration of renewable energies is a rule, a basic rule of the system, you of course have to decrease the production or increase the production of the other production means, and most of them are not as flexible as hydro, for instance. So it really poses a problem to the network managers. This is an example I got from Pierre Pinson from from the Technical University of Denmark for the case of the 25th of December 2012, so for Christmas. I've not put all the curves he provided me, but the idea is that the reference load for that particular day is the blue one, and the forecast they made the day before was this one. So it was anticipated that there would be little wind in the morning, and then the wind would blow, and the net demand would decrease. And in fact, the wind was stronger in the morning, and so the net load is the difference between the reference load and the production from wind energy. And so the picture was this one, in fact, and when you calculate the difference between both, you have a balancing volume of more than 18,000 megawatt hours, which is something like 45% of the daily predicted energy generation. So it's quite huge, it's very important, and it's only a 24-hour forecast. So this poses problems to system operators. And something I didn't mention before, but the general rule for planning your production means is to consider the demand you have forecasted. So you have a given demand you have anticipated for the day before, for the day after, for instance, and then the rule is to use the merit order effect, the merit order rule, which consists simply in using your production means by increasing cost of production. So in the countries where you are obliged to use wind energy, of course it is used first. So you will have this, for instance, this level of wind production available for that day. And then the idea is to use other production means and to add the production of those means as long as you cross the curve for the demand. And so you can see that you can have, for instance, this picture with wind, hydros, and nuclears, and combined heat power, and so on. And if you have a large uncertainty on wind forecast, on the wind power which will be available, of course it can move your curve to the left or to the right, and the effect is that it can totally change the production means that you will have to call to face your demand. And in that case, in the blue case, the most expensive one will be the THP, and if the wind blows a lot, you will use only nuclear, which is much cheaper, but if the wind blows at lower wind speed, you will have to use more expensive production means. And so even for 24-hour forecast, the uncertainty in wind production can be very impactant on the energy prices, depending on the different means of production you will call to face the demand. I will probably speed up with these ones because I think all of you know that. But wind and solar, of course, are highly fluctuating resources, both in time and space. This is an example from La Réunion Island for 4 typical days of production with a clear sky condition, a very cloudy day, a very variable day, and another one which is typical of La Réunion with a clear sky in the morning and then a drop-off of the production. So this is the time varying of the production. And we also have strong variations in space. These are different curves for one site, for a few neighboring sites, a region, and the total country. And of course, you can see that considering the production of all the country, allows to have a compensation of errors. And so it's easier. But when you want to make forecasts at the local scale, it's more difficult. I will go through this because I think many people will talk about that. And the point about wind and solar forecast is that they have a new effect on the load curves. This is once again taken from the IEA Harnessing Variable Renewables publication, and I took this from David René from ICEM 2011. So in this plot, you have an example for the Nordic countries. So the red curve is the classical load curve, which is quite regular. You can see the working days and then the weekend with a small reduction. But when you consider you have to take into account the production by wind energy and solar energy, which are in green and yellow, you can see that the net demand, which is the base, the reference demand minus the production from renewables, gives you this black curve, which is much less regular than the reference one. And so there are many forecasting problems because energy system managers are used to work with such kind of curves and know they have to work with very irregular curves, and it poses many problems to the current models. And you can see even that the net demand can become negative in some cases. It has a strong impact on the management of the systems. This plot from Keith Parks shows, for instance, that the classical error on load for that particular case was 86 megawatts. But when you consider the error due to the wind production, you have a net load with an error which is increased by a factor of 3, which is very important. But the good news is that improvement in wind and solar generation forecast can imply savings. So this is once again an example from the Excel Energy system. We worked with NREL and NCAR to develop a very nice forecasting tool for wind energy. Maybe Sue will talk about it later, either today or during the week. And just to give you an example, with this introduction of this strong and powerful model, they could reduce their minuscule percentage of 3.5% in 1 year, and this allowed them to make $2.5 million savings. So that's good news. So the point about renewable energies is that they will imply a rising uncertainty. And we even talk about intermittency, which is the combination of the generation variability, natural variability, and of the forecast uncertainty on this variable. Of course, we can imagine several ways to deal with that. First, with uncertainty, of course, we need, from the technical point of view, to use additional operating margins at all time scales. That's, say, backup capacity, scheduled capacity margin, and so on. But we also need input from the weather and climate community, especially to provide high-quality data for siting, dimensioning, and investment studies prior to the installation of those facilities. And then we need, of course, a strong improvement in wind and solar generation forecast, which is really essential. And of course, to deal with variability, we need more flexibility, but this is more a problem for the energy people. I will skip climate change adaptation and investment because time is running, and I think it would need another day-long seminar, but we also have concerns in this field. And I will very briefly now show you some different approaches we use just to introduce the next talks by my colleagues. So first, I've put this plot, which is nice. It's from Chocoli, so it's a nice one. And the interesting thing is that it shows the different timescales in weather and climate science. And the interesting point is that it looks like pretty much the timescales relevant for the energy sector, from the intradaily operations to the long-term planning processes. I will not describe all the processes. I've already said many about them. But the interesting information is that when you go from the longer term to the present time, of course, the amount of available information is more and more important, but the problem is that the optimization levels become more and more restricted. And so in all this sketch, we have uncertainty almost everywhere, The kind of uncertainty can vary from one time scale to another, but there's uncertainty anywhere. We'll skip this one. Just a few slides to show you some data we use. Of course, observations are very important, both climatology, but they are also important for model initialization, assimilation, calibration, and verification. And this, in general, are used to make long-term planning, investment, and resource mapping. I think Richard will talk about resource mapping. We need good data sets to estimate the bankability, for instance, of a solar farm or PV farm, a wind farm, and so on. But data are also very important for new real-time system management, monitoring, and verification statistics afterwards. So I have briefly two examples. The first one is a downscaling with a high-resolution model from reanalysis. And the other one is a data cleaning process run by Meteo France. These are basic climatological data which have problems which can be homogenized to get a much cleaner picture. Data are, of course, very, very important for the short-term and very short-term management of wind and solar generation. This is, for instance, a weather station we developed for La Réunion Island in the Indian Ocean. So we have classical sensors, and the new things on this is that we use a lot of cameras. So we have a fisheye camera and different sky cameras. I will, show you just all. Yeah, if I can. Yeah. Okay, that's it. So this movie shows you the fisheye camera, which is pointed toward the vertical, and these are 5 different cameras pointing at different directions. And this is the measurement of solar radiation. I will go forward, but what you can see is that in La Réunion in particular, because we have a sharp orography, we have convective developments at midday in particular. And what you can see is that the meteorological situation is very, very complicated. And so there are big challenges to try to forecast such events. And much research is really needed to help in this field. I will not go further in the movie. The interesting point is that some of my colleagues developed algorithms to use the images from the camera, from the fisheye camera, and they could develop a method to compute the solar radiation from this data. There will be a talk by Bruno Charbonnier. I think it's on Wednesday. And once you have the image, you can use algorithms to make a segmented image, and then you can recompute the solar radiation, and you can even reproject the image on a map. The wind farm, the PV farm is there, and then you can see the clouds here, which are arriving on the system. And the next step is to be able to forecast the evolution of the sky situation over a few minutes. Of course, weather forecasts are really useful. Here it's again the example of the NCAR system for Excel Energy for wind production, which is very complete, very, very interesting. I will skip briefly. One important point is to help people in the energy sector to use probabilistic information rather than deterministic. Because, of course, when you want to look at timescales longer than a few days, you have to be probabilistic. This is just a short example. I've already showed a number of times, but these are 2 forecasts from ICEM-WF from the ensemble prediction system. You have the temperature there, and the colors all for the percentage of the 51 members forecasting a given temperature. The red one is the ensemble mean, and the green one is the observation. And you can see that in this case, if you take the ensemble mean as a single deterministic forecast, it's quite, it's nice forecast. The overall is very moderate. But if you take the other situation where you have a bimodal distribution of the forecast, with the verification being in this part, If you take only the deterministic information from the ensemble mean, you make a maximum error of more than 7 degrees, which is very important and which corresponds to a strong error in demand forecasting. But of course, we have a strong difficulty with probabilistic forecast, which is that it's very difficult to integrate in existing tools, in particular in big models as the one we have at EDF. And so much work is needed to help people using this information. Well, I've already presented this in many conferences, so I will go very briefly, but we also use, for instance, ICEM-WF monthly forecast for geopotential and a post-processing method based on analogs to make stream flow probabilistic forecast. And as you can see on the picture, this helps reducing the uncertainty on the stream flow. So the green are for stream flow climatology. The red curves are the hydrological model, which is forced by historical time series of temperature and precipitation. And the blue one are the new method using ensemble prediction system from ICEM-WF. And you can see that the uncertainty is highly reduced. And this method is now operational at EDF. Yeah. From seasons to decades, to some decades ahead, of course, we can use different kind of information. For instance, in France, we use extended present-day climatologies, which simply consist in computing the linear trends over the last 30 years and extrapolating them for the next decade. But we also use reanalysis. This is another example from Meteo France, from Jean-Pierre Serron and Stéphanie Singla, who defended a PhD a few months ago. About the use of seasonal predictions for hydropower and water resource management in France. The general idea, we're not going into details, but the general idea is that seasonal forecasts, of course, in mid-latitudes are not very skillful, especially for precipitation. But when you go to applications model, and for instance, when you look at soil wetness index or river flow, you get some skill because it is an integrated variable. It integrates different parameters, and so you can find some skill there. This is an example about seasonal forecast. I will skip this. Decadal prediction, I won't say anything about that because I think it's still at its premises, and the science is developing, but I don't think applications are for today, but we have a careful look at this. And I will skip again climate change. You will find the slides in the presentation, which will be available because I'm short of time. And I now come to my short conclusions. What I'd like to insist on is the fact that really with the development of renewable energies, and in particular wind and solar energy, the energy sector in general in most countries will really be more and more dependent on weather and climate. So you can find many scenarios of the evolution of the energy mix in different countries or for the world. This one is the example from the World Business Council for Sustainable Development, which is an international council of different energy producers and transmission system operators and so on. And you can see that the renewables are rising a lot in this one. You can have a look at IEA scenarios and so on, and in any case, renewable energies are going to play a very important role in the next decades. So the energy systems will really rely more and more on those energies, and they will be more and more dependent on weather and climate. So there is really a strong place for collaboration between energy and meteorology. Of course, energy companies have been working with people from meteorology for a long time. For instance, at EDF, we've been working with Meteo France for more than 30 years now. But the good news is that, let's say, in the last decade, there were many initiatives to foster, to develop the collaborations. And I think Alberto and some of his colleagues were really leaders in this field. With, for instance, this workshop held in Italy in 2008. Then we have seen the development of energy meteorology session in some conferences. In the EMS, it's the same in the AMS in the US and so on. And now we had the first ICEM 2 years ago, and we have this one this time. And we see more and more projects. For instance, the CleanRun and UPOLAS projects, which are European projects, dealing with the application of science towards applicated sectors, and especially the energy sector, which is, I think, one of the most demanding of such applications. Well, I think it's time to conclude. And so what I'd like to say is always the same message in my talks. I'm sorry, but I really think it's very, very important. So in the last, I put 10 years, but I think it's in the last years, I don't know how many, really much progress has been done in national med services and research centers and academics. And I really believe that the essential point to run applications, to develop useful products, is really a dialogue between providers and users. For instance, EDF and Meteo France, I think, is a good example. And this kind of collaboration really allowed many improvements, even if problem remains, for example, in the use of probabilistic forecast, but whatever. The collaboration is essential. And for this, communication and training of end users is really, really very important. And what I've not put on the slide, but I should, is that I think training of people from the training of med people, climate people from the application sectors is also essential. And so providers and users really must work together, but not downstream. They must work upstream to develop tailored products, useful products, and maybe also with other people from other domains like statisticians, social science people, and so on. And so I think this seminar and this conference will be a great opportunity to network all together, and I really wish you a nice seminar, next time conference, and please work together. Thank you.